Welcome to your AI Academy. In today's video, we're diving into the core sciences and mathematics that are essential for mastering artificial intelligence, AI, and machine learning. If you're on the path to becoming an AI engineer or data scientist, you've probably heard that subjects like linear algebra, calculus, probability, and discrete mathematics are crucial. But why exactly are these fields so important? In AI, we'll explore how concepts like matrix multiplication, eigenvectors, and SVD help us reduce dimensions and transform data. Next, we have calculus, which is all about optimization. Whether you're training a neural network or tweaking an algorithm, you're using derivatives and gradients to minimize errors and maximize efficiency. I'll show you how these ideas fuel techniques like gradient descent. We'll also break down the role of probability and statistics, which allow AI models to make predictions and decisions in uncertain environments. From Bayes' theorem to hypothesis testing, these tools help build powerful AI systems that can handle complex data. Finally, whether it's graph theory or combinatorics, you'll see how these concepts help AI models navigate networks and solve real-world problems. By the end of this video, you'll have a clearer understanding of how each of these mathematical foundations plays a vital role in AI. So let's jump in and get started. Mastering the core sciences and mathematics is crucial for AI engineering because it provides a theoretical foundation upon which machine learning algorithms, deep learning architectures, and AI systems are built. Here's an in-depth look at the important topics and how they relate to AI. 1. Linear algebra. Linear algebra is fundamental to many areas of AI, especially in understanding how data is structured and processed. Concepts from linear algebra appear in virtually every AI algorithm, particularly in machine learning and deep learning. Key topics: vectors and matrices represent data, weights, and transformations in models. For example, in neural networks, inputs, weights, and biases are often represented as matrices. Matrix multiplication, key to transforming data and performing operations in neural networks and graphical models. Eigenvalues and eigenvectors, important in dimensionality reduction techniques like principal component analysis, PCA, which is used to reduce the feature space. Singular value decomposition, SVD, used in recommendation systems and compression techniques. Application in AI. In deep learning, matrix operations are used in each layer of a neural network to compute the output. For instance, a simple forward pass in a neural network is a series of matrix multiplications and additions. In machine learning, algorithms like support vector machines, SVMs, rely on inner products between vectors, a concept from linear algebra, to classify data. How to study. Books, Linear Algebra and Its Applications by Gilbert Strang. Online resources, Essence of Linear Algebra by 3Blue1 Brown, YouTube series. Practice, use libraries like NumPy or a TensorFlow to perform matrix operations programmatically. Yamiyasabwabumi Hums 2. Calculus. Calculus is essential for understanding how AI models learn. Many AI algorithms rely on optimization techniques, which are calculus-driven. Calculus helps in minimizing or maximizing functions, such as finding the best weights in a neural network. Key topics: derivatives and gradients, used to find how changes in inputs affect the outputs of functions. In AI, this is crucial for backpropagation in neural networks, which optimizes the model. Partial derivatives. When dealing with functions of multiple variables, as is common in AI, you'll need to calculate how changing one variable affects the output while keeping others constant. Gradient descent. The core optimization algorithm in most machine learning algorithms. It uses gradients to iteratively adjust model parameters to minimize a cost function. Chain rule. Crucial in backpropagation, where the error in the neural network is propagated backward to update weights. Application in AI. Gradient descent algorithm. In training neural networks, calculus is used to compute gradients of the loss function with respect to the model's parameters. These gradients are then used to update the model weights, allowing the model to learn from data. Convolutional neural networks, CNNs. In CNNs, derivatives are calculated to optimize the feature extraction process. How to study. Books, Calculus by Michael Spivak, or Calculus for Dummies for beginners. Online resources. Khan Academy's courses on calculus, MIT's OpenCourseWare for multivariable calculus. Practice, implement gradient descent manually to reinforce the concept. Mamajauka Phase 3, probability and statistics. AI involves making predictions and decisions under uncertainty, which is why probability and statistics are critical. These disciplines help you understand data distributions, make predictions, and evaluate model performance. Key topics: random variables and distributions. Understand normal, binomial, Poisson, and other distributions to model different types of data. Bayes' theorem, a foundation for probabilistic models like naive Bayes classifiers. Bayesian reasoning is also used in machine learning models for uncertainty estimation. Expectation and variance, used to understand the spread and behavior of data, which is vital for evaluating model outputs. Hypothesis testing, important for making inferences about data, ensuring that models generalize well to unseen data. Markov chains and hidden Markov models, applied in sequential data problems such as speech recognition and time series analysis. Application in AI. Naive Bayes classifier, one of the simplest yet highly effective classification algorithms based on Bayes' theorem. It assumes independence between features, and despite this assumption, it performs well in many real-world scenarios. Probabilistic graphical models, PGMs, used to represent conditional dependencies between variables and are used in areas like natural language processing, NLP, and vision. How to study. Books, Probability and Statistics for Engineers and Scientists by Walpole. Online resources, Probabilistic Graphical Models, course on Coursera by Daphne Koller, Khan Academy for Probability Fundamentals. Practice, work on classification tasks using algorithms like naive Bayes and Bayesian networks. Fourth, discrete mathematics. Discrete mathematics is particularly useful in algorithms, data structures, cryptography, and combinatorics, all of which are important in AI. Key topics: combinatorics, study of counting, permutations, combinations, and graph theory. Essential in problems where you need to optimize or analyze discrete structures. Logic and Boolean algebra, logic gates, truth tables, and logical reasoning are fundamental to AI algorithms and computer architecture. Graph theory, graphs are used in AI to represent networks, state spaces, and relationships between entities. Common AI applications include social network analysis, shortest path algorithms, and decision trees. Set theory, important for understanding data relationships and operations in databases. Application in AI. Search algorithms. Algorithms like A-star or Dijkstra's, which are used in game AI, robotics, and pathfinding, rely on graph theory and combinatorics. Logical inference. AI uses propositional logic for reasoning systems and solving puzzles or decision-making tasks, e.g. expert systems. How to study. Books. Discrete Mathematics and its Applications by Kenneth Rosen. Online resources. MIT OpenCourseWare on Discrete Mathematics, tutorials on graph algorithms. Practice, implement graph-based algorithms like breadth-first search, BFS, depth-first search, DFS, and shortest path algorithms. 5. Optimization theory. Optimization theory is fundamental for machine learning because most algorithms involve minimizing or maximizing a cost or objective function. Key topics: convex optimization. Many optimization problems in machine learning are convex, meaning they have one global minimum, which makes them easier to solve. Lagrange multipliers, used in constrained optimization problems, where you have to optimize a function subject to certain constraints. Stochastic optimization, key to large-scale machine learning, where stochastic gradient descent is used to optimize models efficiently with large datasets. application in AI training. Deep neural networks. Optimization is the process of tweaking the model parameters to minimize the error on the training data, using techniques like gradient descent. Support vector machines. The optimization of a separating hyperplane in high-dimensional space is a convex optimization problem. How to study. Books. Convex Optimization by Dory and Vandenberger. Online resources. Stanford's CS229 machine learning course and resources on Coursera for optimization methods. Practice. Experiment with optimizers like Adam, SGD, and RMS-PROP in TensorFlow or PyTorch. Final tips for mastering core sciences and mathematics. Solve real-world problems. Apply your knowledge of these subjects to real-world problems. This will make your learning more practical and reinforce the theoretical concepts. Practice consistently. The key to mastering these subjects is regular and consistent practice, especially in the areas of calculus and linear algebra, where intuition builds over time. Study AI algorithms. Once you've built a foundation, start studying how AI algorithms leverage these concepts. This will solidify your understanding and give you insights into why these subjects are so critical.